Analyzing bonds with embedded options requires understanding a shifting financial power dynamic. Callable bonds grant the issuer a leash to pull the debt back early, while puttable bonds provide the investor an eject button to exit the position. This 2-year interest rate tree for a 7% $100 par bond is our baseline. We calculate this straight bond's value using backward induction, discounting from the right side back to today. Always add the coupon payment to the node before applying the discount rate. The completed math reveals year-one node values of $99.83 and $101.59. Once we discount those back one final period, we arrive at a node zero present value of $102.99. This $103 price serves as our anchor. It represents the pure time value of money and credit risk, isolated from the distorting effects of embedded options. If this bond is callable at $100 in year one, the issuer gains a ceiling. They will exercise their right to call a bond whenever the theoretical node value exceeds $100, effectively capping the investor's potential payout. At the lower node in year one, the theoretical straight value is $101.594. Under the call rule, the issuer overwrites this value, replacing it with the $100 call price. Pause the video here. Using the upper node value of $99.830 and our new capped value of $100, use the backward induction formula to calculate the new value for node 0. Factoring in the call cap, the current value of the bond drops to $102.238. This lower price is the investor's compensation. The market demands a discount upfront to account for the risk that the issuer will exercise their call. Puttable bonds use the opposite logic. The investor exercises the put if the node value falls below $100, creating a hard floor. This floor pushes the 99.83 node value up to 100, resulting in a higher overall bond value of 103.08. We can use these results to isolate the exact value of the embedded options. Subtracting the callable bond price from the straight bond gives us the value of the call, while the puttable bond's price minus the straight bond reveals the value of the put. From a valuation perspective, a puttable bond is an insurance policy where the investor pays a premium, while a callable bond is a right sold by the investor in exchange for a discount. Option pricing is inextricably linked to interest rate volatility. Any increase in expected volatility directly raises the theoretical value of both call and put options. This rising volatility drives the two bond types in opposite directions. Because the investor is short the call, rising volatility pushes callable bond values down. Since the investor is long the put, that same volatility lifts puttable bond values. This relationship is central to the option-adjusted spread, or OAS. The OAS is the constant spread added to the model to force its theoretical price to align with the actual market price. If an analyst underestimates volatility, the model undervalues the call option. This artificially inflates the model's bond price, requiring an oversized OAS to bridge the gap between the model and the market. Underestimating volatility masks the true risk of the option, presenting a fairly priced bond as a massive bargain. These phantom discounts lead to capital allocation mistakes that can destroy portfolio value. The asymmetric payouts of these options break standard effective duration. To get an accurate picture of interest rate sensitivity, analysts must use one-sided durations to see how the bond reacts to rates rising versus rates falling. Standard bonds and putable bonds exhibit positive convexity. As yields decrease, their prices rise at an accelerating rate, creating a curve that bows outward. Callable bonds deviate as yields drop toward the call price. The price hits the issuer's ceiling, forcing the curve to flatten and bow inward. This is negative convexity. Negative convexity represents the structural penalty for the bondholder. They absorb the full downside when rates rise, but their upside is strictly limited when rates fall. A bond's coupon indicates which rates drive its value. Low coupon bonds rarely trigger calls and behave like straight bonds, sensitive to maturity. High coupon bonds face a high probability of being called, making them most sensitive to the time to exercise rate. By applying the binomial tree framework, you transform embedded options from hidden risks into quantifiable variables you can price with precision.